Hiya. Parametric equations is what I'm going to do next. And you might think, hang on, I've done that. Yeah, you have. But of all the chapters that I didn't do, this is the one that I kind of missed most, I suppose, because I like doing this chapter. It's really, really nice. Opportunity to do some really wonderful graph sketches, and some of the best graphs, or best looking graphs, in the pure course come up from this chapter. It's kind of difficult for me to say, I won't do that. Yeah, so this one here, for example, this is question 4b from one of the exercises. Your x equals 3 root t, y equals t cubed minus 2t, t is between 0 and 2, you've got to sketch the graph. Okay, so I know the answer in the back of the book, I know you've probably done it, but let's just see what happens, let's just see what method I take you down, okay? I never use tables of values. I don't really like tables of values, okay? A very, very last resort. I still don't like doing them, okay? So, let's just have a look at this. I want to rearrange that, so I'm going to make it root t equals x over 3. I can put that in there, you see. But I need an expression for t cubed, don't I? So t is equal to x squared over 9. So that means then that t cubed would be x to the power of 6 over, that's not nice, is it? Okay. So that's going to be 3 squared cubed, 3 to the power of 6. Yeah, that's better. But then, do I really want to substitute that in? Not really. I'd rather just make it a little bit simpler if I can. So that it's t squared minus 2, and then it should be a little bit nicer than having x to the power of 6 in it. So t is that, x squared over 9, and then t squared is, well, what's that going to be? Rather than have t cubed, let's have t squared. So if I write that as 3 squared again. Okay, so square that would be x to the power of 4, and then 3 to the power of 4. So x to the 4 over 3 to the 4 minus 2. There we go, that's my Cartesian equation. And who doesn't want to sketch that? Come on. Yeah, I don't really need this anymore. Okay, so I'll just, I'll get rid of that. Okay, so it's that, and then y equals x squared over 9, x to the 4 over 3 to the 4 minus 2. Okay, now the first more obvious thing to do is to find where the x-axis crossing points are. So let's see what happens when y equals 0. Okay, so y equals 0, you have x squared over 9 equals 0, of course, therefore x is 0. Or you're going to have x to the 4 over 3 to the 4 minus 2 equals 0. So you're going to have that. Okay, you have x to the 4 is equal to 2 multiplied by 3 to the 4. 3 to the 4 is 81. So that's, okay. Actually, no. No. I'm going to keep it as 3 to the 4 because I'm going to do the 4th root of both sides, aren't I? So x is going to be equal to the 4th root of 2 multiplied by 3. Yeah. Calculator time, because I don't know the 4th root of 2, unfortunately. Or fortunately. Oh, how do I do this? Oh, flipping heck. Sorry. Yeah, okay, here it is. Right, 4th root of 2. You can see I don't use a calculator that often. Times by 3 equals 3.567, you agree? Yeah. So x equals 3.567 ... Yeah. What's the y value going to be? Okay. So put this there for a moment in case I need it. So the y coordinate would be y equals x squared over 9. So that's squared. Okay, so 2 to the power of a quarter squared is 2 to the power of a half. So that's root 2 over 9. And then x to the 4 is just that, isn't it? 2 times 3 to the 4. Oh, what the hell am I doing? Trying to find the y coordinates. Bloody well 0, isn't it? Scrap that. Yeah. That was a moment of silliness, shall we say. Okay. Right, the y coordinate is 0. Because I'm trying to find the x coordinates, aren't I? Okay, so I'm just going to make a note of that then. So 0, 0 and 3 point, I think we can go at 3.6 to sketch 0. Okay, those are the only crossing points. Okay, now granted you could possibly have positive or negative x equals 3 point, which is kind of interesting. Okay. However, if I have x as a negative value, that would imply then that this here would be negative. And can you see from the right hand side, there's no value of t, that would give us a negative value of x. Okay, so x is going to be positive only. Okay, you can make a note of that if you want, but there you go, x is going to be positive or 0 only. Okay, that kind of helps us because we know which parts of the axes we're dealing with. We're only dealing with the values that are positive for x. Okay, y on the other hand could be positive or negative. Okay. Why is it going to be positive or negative? Well, simple really, because there's two x-intercepts. To get from one to the other, it's got to go, I would say, below the x-axis in order to connect up. Do I need, maybe I need the Cartesian equation. Okay, I'll just keep that for the moment. Okay, so let's just write that a bit higher up, like that. Okay, there we go. Okay. Alright then, so what do I know about the curve then? So let's just do a quick sketch. It's going to be there, and what does it do? What does it do afterwards? Well, I know that as x tends towards infinity, y is also going to tend towards infinity, isn't it? Okay, because you've got a very large power there, x to the power of 6. Okay, so it's going to have to be doing this. Up there. Okay. So my guess is it's going to do something like this, but it's been an unusual type graph. Okay. Is it going to do that? Or will it do something slightly different? Okay. We're going to find out, aren't we? And there's a definite minimum point there, isn't there? Where is that minimum point going to be? Is it going to be right in the middle? You know what we need? We need calculus. We need calculus to do this. We have to use calculus. So, do you want to do parametric differentiation or Cartesian differentiation? That is not really that difficult, is it? Let's face it. Okay, so we'll do Cartesian. So y equals x to the power of 6 over, I'm going to have to do this, 3 to the power of 6. Subtract 2x squared over 9, and differentiating that is not a problem. So dy dx is 6x to the 5 over 3 to the 6. That does not look like 3 to the 6, does it? 3 to the 6. Subtract 4x over 9. I want to set that equal to 0. Let's just write that as 3 squared, shall we? Okay, so what am I going to have? I'm going to have 6x to the 5 over 3 to the 4, subtract 4x equals 0. Yeah. I can write the 6 as 2 times 3, of course. And then I can just cancel one of these, make that 3 cubed in the bottom, and I can divide both sides by 2. Okay, hope you followed all of that. So we've got x to the 5 over 3 cubed minus 2x. I can then factorise that, x and then x to the 4 over 3 cubed, subtract 2 equals 0. That gives me either x equals 0. That's really interesting, isn't it? It's really interesting, because it means that there's a stationary point at the origin. Okay. Or we've got x to the 4 over 3 cubed is equal to 2, so bring the 3 cubed over to that side. 3 cubed is 27, times that by 2 is 54. Yeah, and then you have x is the 4th root of 54, and I'm sorry, I cannot do that in my head. So let's do the 4th root of, I know where that nth root button is now, because I've just used it. So 4th root of 54 is 2.71. Okay, 2.71 dot dot dot. Okay, there we go. Well, I know that when x is 0, y is 0, because we had that as an x-axis crossing point. I don't have the y-coordinate of this though. Okay, so the y-coordinate, I'm going to put it into here, aren't I really? Okay, So it's kind of fiddly. Yeah. Sorry, it's time consuming. I'm gonna have to do this. Okay, so I only need it to one decimal place really. So let's just do that. Okay. So pals, bear with me. Sing a song or something. Can't use a bloody calculator. This is what I normally say to someone, can you please work this out for me and just tell me what it is, because I've just mucked that up. So sorry, do this again. Okay. Alright, let's get that thing up. 4 through of 54 equals that. Okay, well let's just square it, shall we? Square that equals, let's just divide that by 9 equals that. So I've messed that up again. How many times have I messed this bloody thing up? So 4 through of flipping 54, because I know what it is now, it's 2.718. Alright, okay, good. Let's square that. That times 2 divided by 9. Right, okay, so 1.63299, that will do. Okay, 4 through of 54. Alright, power 6 divided by 3 to the 6. Right, 0.5, right, so subtract 1.63299. Okay, you're not going to argue with this, are you? Negative 1.09? Okay, if I got that wrong, I'm sorry, but that's what I'm going with. Okay, it kind of sounds right as well. All right, so where does that leave me with? Okay, all of that information. Okay, well, let's just have a look at sketching this. Okay, so I only need this part of the graph, don't I? I'm hoping that you can kind of see that nicely. Okay, I know it crosses there, the origin, and I know it crosses there at about 3.60. Okay, and I've worked out that there's a stationary point there. Okay, if the graph is doing this, that's not going to be a minimum point, is it? And I pretty much doubt it's a point of inflection, to be honest. I reckon it's a maximum point. You can check that. You can check that. But I'm reckoning, in fact, no, I'm not reckoning. I know the graph is symmetrical about the y-axis. Maybe I'll mention that in a minute. Okay. How do I know it's symmetrical about the y-axis? Good question there. So there's going to be a maximum point there, all right? And I worked out there's another stationary point here, 2.7, so that's over the halfway bit, isn't it? So let's just put that there as 2.7, negative 1.09, so somewhere there. So there's a minimum point there, and then it goes past that, and it goes all the way up to infinity. There. That's what the graph looks like. Okay, and we know the coordinates of that minimum point. That's kind of lovely, wasn't it? But this is far more interesting than doing a table of values, don't you agree? Because I know exactly where that minimum point is now. I've proved that that's a stationary point. You could almost say I've proved it's a maximum point. Okay, I know exactly where that is. That's great. How do I know this is a symmetrical about the y-axis? Okay, it's quite simple. There's a quick test that you can do for this. Rather thought it's some lovely maths. Okay, but I don't need it anymore. The purpose which it has been done has been served. There's a quick test. Okay, if f of negative x is equal to f of x, then it's symmetrical about the y-axis. Kind of nice. Okay, you can see that when x is negative, here, you get exactly the same values if y was, so as if x was positive. Okay, so that being the case, it's reflective. It's got line of symmetry about the y-axis. What that means is that it couldn't have been a point of inflection. It couldn't be doing that because then the graph would not be symmetrical, would it? The whole thing would have to do this there and then like that again. It'd be kind of like a W-shaped graph, which is kind of cool. Okay. Anyway, hope you found that interesting. I did.